Okay, good morning, good afternoon, good evening, everyone, and welcome to our next episode of the YugabyteDB Friday Tech Talks by engineers for engineers. I'm Kannan, a co-founder at Yugabyte, and it's my pleasure to welcome Anand as a speaker for today's topic. Anand, love for you to go ahead and introduce yourself and the topic for the day also. You're on mute right now, by the way.
Yep. Yeah, thanks, Kannan. So hello and welcome to all. My name is Anand Srinivasan. I've been in the industry for about 24 years now, working with data all the time. Started off with databases, then worked with data stream query processing, ETL, real-time data warehousing solutions, change data capture. I was with Oracle for about close to 19 years. During the time I worked on all of these products. And I joined, it's been about 9 months for me at Yugabyte, and I've been working on change data capture at Yugabyte.
And yeah, great to have Anand at Yugabyte. We worked together in the 90s at Oracle back then in the database team. So fond memories of that as well. And really delighted to have a database expert today talk about this topic. And yeah, thanks, Anand.
All right. Okay, so we get going. The topic for today is transactional change data capture. During the course of this talk, we'll see what is transactional CDC, what is the key requirement that it addresses, and how it goes about doing that. Yep. So we'll just start with a really quick and short introduction of change data capture itself. CDC is the process of identifying and capturing changes made to data in a source database, and then delivering those changes, if required, in near real time to downstream systems like data warehouses, data lakes, operational data stores, and so on. And it figures in a variety of use cases. It's used in a variety of use cases, starting from a direct data replication use case, or if you want to load a system wherein you want to do analytics, reporting, more advanced analytics. It figures in many microservice architecture patterns, in use cases like online live migration, and so on. And the list is, and many more such use cases. In many of these use cases, there is a very important requirement, and that requirement is one of data consistency in the downstream system, in the system from which you are loading the data from the source. And so what exactly does this data consistency in the downstream system mean? It means that the data in the downstream system needs to either be, if it's like a plain replication, it either has to follow the same consistent states of the source database, or if it's a transformed form, it has to be based on the consistent states of the source database. And we'll take and what does this give? If this data consistency is there in the downstream system, what it actually gives is, it gives ACID reliability, not just in the source system, but across the systems connected by CDC. So let's take a look at a simple example, a very simple example that gives a better appreciation of this data consistency requirement. And we'll actually do that by looking at the opposite, by looking at what constitutes inconsistent or data that is not consistent. So we'll take a very common example here, orders and order lines. And let's say that's your source database. You have an orders database. So you have an orders table and an order lines table. The orders table obviously is the parent table, one row for every order. And your order lines table has one row for every line item. So as many rows on the order line tables as the line items in the order. And obviously there is a parent-child relationship with the order ID with order lines having a foreign key to the orders table. Now let's suppose your source database has the following states. It was empty, then it had the first order come in and the second order come in. But in the process of moving data on the target system, you ended up with a state where you had the line items from both transactions, but you have only the order from one of the transactions. And further, your applications, let's say the application is trying to do analysis of these orders. And this inconsistent state on the target system is visible to applications. And the analysis happens, and let's say that somebody is trying to figure out what is the average value of an order, what are the average number of lines in an order. And all of this is based on the data in the target system, which is not really representing the source data. And naturally, all the conclusions and the answers are going to be misleading and unreliable. And this is exactly what is sought to be avoided. So CDC that moves changes, that a CDC solution that moves changes to the target system while ensuring consistency in the sense relative to the source system, as described a little while earlier. This type of change data capture solution is referred to as transactional CDC, with the data consistency being the key requirement that it addresses here. So how does transactional CDC solution look like, and how does it go about addressing this requirement? CDC in general has two phases: a snapshot, an initial snapshot phase, followed by the streaming phase, this continuous streaming phase, which keeps going on and on.
So, Anand, maybe, sorry to interrupt, one question. So is it fair to say that before this capability, Yugabyte has had change data capture feature even prior to transactional change data capture? Is it fair to say that the transactional guarantees were weaker and primarily kind of at a per shard level consistent rather than multi-shard or multi-table consistent?
Yes, that is correct. That is correct. So prior to this, Yugabyte had consistency at a per shard level, but not at a multi-shard or a multi-table level, as this example would sort of require.
Thank you. Yeah.
Now, so there are two phases, snapshot and streaming, and both the phases, there is a role to play in both the phases to ensure transactionality or data consistency. In the snapshot phase or consistent snapshot phase, to emphasize on the consistency aspect, what happens is that a particular state of the source system is identified to be and it's identified as your consistent point. And what that means is the goal is going to be at the end of the snapshot phase to get the target system to this initial consistent point. And once that is done, so you start off now, your target system is at a consistent state relative to the source. It is at this state which we refer to as the consistent point. And then we're just going to continue to maintain consistency by replicating the source transactions in order. And this is the broad idea. So if we drill down a little bit deeper into consistent snapshot, what happens is typically this might happen at the time of stream creation. So you create a CDC stream, that is going to be the vehicle through which the changes are going to get streamed over. So at the time of stream creation, let's say you pick a state on the source database and you mark or identify that as the consistent point. Now, this consistent point is going to serve as the boundary between the snapshot and the subsequent streaming. So basically everything is going to get covered. Everything up to the consistent point will be moved as part of the snapshot process or a part of moving the snapshot data. And everything subsequent to the consistent point will be streamed out as streaming changes, which will be consumed in the streaming phase. Now, the key point here is actually during snapshot consumption. Now, after the creation of the stream, before the snapshot consumption may start, or even during the snapshot consumption, remember the snapshot consumption is going to take some time because you might be moving terabytes of data as part of the initial snapshot. The source system is going to be active. There are transactions happening all the time. I mean, sort of a glimpse of what we saw in the, we saw in that simple example that we had taken before. But during the snapshot consumption, the snapshot data that is going to be loaded from the target is only going to be from that fixed consistent point. The fact that there is more changes happening in the source is not going to matter. And so at the end of all of this, at the end of the snapshot consumption, we meet our goal of getting the target to or based on the consistent point. So if we look at it in terms of the example that we just saw before, so you have your first order, let's say at this point, your stream is created. And this state of the source database is identified to be the consistent point. So essentially, we want to get this state replicated on the target at the end of the snapshot consumption. Now the snapshot begins. The source, of course, is active all the time. You get more transaction coming in. But nevertheless, that doesn't come in the way that when you load the data for the order lines table, it is from that consistent point. And at the end of the snapshotting process, we've achieved what we set out to achieve, which is our first target of getting the target to the initial consistent point. And I guess it's a good time now to sort of jump in and see whatever we have seen. So whatever we have talked about so far in action. So we'll move in and to the demo here. We'll see the consistent snapshot, and also we'll take it further into the consistent streaming as well. So the demo is involves loading a target system without having to disable constraints on the target. And the flow, the pipeline is as follows. We have a Yugabyte source universe here, and the target is going to be Postgres. We have a source Yugabyte source Debezium connector, which is going to move the changes, which is going to move the snapshot and then the changes from the Yugabyte source universe to Kafka. And then we'll use a JDBC sync connector, which moves the changes from Kafka to Postgres. So let me just move over here. So the screen on the left top, this is going to be my this is my session to my source universe. So let me just see if I yeah, okay, this is fine. Okay, so I'll create my orders and order line tables, which is identical to the schema in the example that we were seeing before. When I'm creating the order line tables, I'm going to create 2 tablets for the order line tables because it's going to be useful for the demo and for the discussion. So we've got our 2 tables here on the source, and I shall create the target tables on Postgres. It's identical structure with a replication example. So you have orders and order lines. Of course, Postgres will not have the split into 2 tablets, but it'll just have the 2 tables. Okay, so let's just see that we got our tables created. Okay, so the next step is let's get some transactions going. So here's the first order on the source database. And at this point, we will create our change data capture stream, CDC stream. So for that, we will use the YugabyteDB tool and use the create change data stream API. And the argument corresponding to the snapshot is here. We'll discuss, I'll proceed for the moment, but we'll come back to this API a little later during the talk. So we use this tool to create the stream, and the stream has been created, and this is the stream ID that we've got. Now, before we...
Anand, one question just for clarification. Without the use snapshot option, is it fair to say that you're only capturing the new data, whereas use snapshot option is the one that is saying, hey, the table already has data, I need to capture that as well?
That's correct. So we support 2 options. Like if the client has an interest in consuming the snapshot data, then you got to create the stream with the use snapshot option. Otherwise, you create a stream with an option called the no export snapshot.
In which case, we get the change, the future changes.
The streaming changes, where the client is clear that they just want the streaming changes.
Got it.
So as we, so now what we'll do is before we consume the snapshot, so we will create another order in the source. So remember that this is the point of stream creation, and this state on the source database, where there's basically just one record in the orders table. This has been now identified to be my consistent point. And this is what we seek to get our target to. Okay. So, but we'll just put in a second transaction, second order that comes in. So this is like, you imagine that the source is active while before and during the consumption of the snapshot. Okay, so we've got two orders on the source now. So we come here now. So now is the time to deploy the connectors. So the connector gets associated with a stream. And the consistent point, remember, is associated with the stream. When the stream was created, it saw what is the state in the source database and associated that as its consistent point. So I'm just using a script here. Actually, what's happening while deploying the connector is that it's using a REST call to Kafka Connect, and it's got a bunch of configuration properties, which we shall go through in a little bit more detail later. So at this point, what we've got is we've got the source Yugabyte connect Debezium connector to deal with the snapshot deployed on Kafka. So let's go to Kafka. Let's look at what's that here? The control center UI interface that Kafka provides to see. So we've got our cluster. So let's see our topics. And we've got two topics here, one per table. So DB server 1.snapshot.public orders is the topic into which the snapshot data for the orders table would have moved. And snapshot.public.orderlines is the order lines table. So let's see what's there in the messages over here. And we've got our order. So remember, the source database at this point in time actually has two orders, but our consistent point was identified when it had one order. And that's why we have seen that the source connector has moved the data from the source database into the Kafka topic, but it's actually moved one order, the one corresponding to the consistent point. And if we look at order lines, it just has two messages. These would correspond to the two order lines of the first order. So nothing about the second order. So this is as far as Kafka is concerned. Now we need to deploy the sync connectors to move the data from Kafka into the Postgres target. And let's do that. At this point, we've got the target system to the same consistent point as we had identified, and which was the goal that we set out for. Okay. So now what happens to the second transaction that we put in here? Remember, we said that the consistent point is the boundary. This cannot get missed. So this will therefore have to become the first streaming change. And let's see what happens there. So to do that, we deploy another connector, another Yugabyte source connector, Yugabyte source Debezium connector to deal with the streaming changes. Okay. And let's also finish up with this, the sync connector, and then we should see, yep, we see the order lines for the second order, and we see the two orders as well. But what's more interesting is what happened in Kafka. So let's go to Kafka. So in Kafka, there is a single topic for the streaming changes. Okay, unlike for snapshot where there is one topic per table, here there is a single topic for streaming changes, and we'll see why that is the case soon. So if you look at the messages, you've got a bunch of messages, and actually I think this might be a good time to sort of head back and look at what's actually happened in the streaming phase in a little bit more detail. We can see the messages here, but this might be a more convenient view. And so you see the messages here. So this corresponds to the second order. The orders record goes first, and then the order lines record. So it's exactly in the same order as it was in the source transaction, and there are begin and end transaction markers also placed on Kafka. So what's actually happening here? So that's it. Let's go back and see what is what actually happened under the covers. Okay, so there are two main aspects that consistent streaming deals with to ensure this consistency, and both are related to ordering. One is intra-transaction ordering and the other is inter-transaction ordering. And so let's see what both of these mean. So here's the second order, which became the first streaming chain. So this was the order, right? There was an insert into the orders table, and there were two line items for this order. Now, what we have here is your Yugabyte universe. And if you remember, we created the order line tables with two tablets. And so that's what you see here. Tablet 1 for the order line tables and tablet 2 for the tablet 2, the second tablet for the order line tables. Orders table, on the other hand, has just one tablet. So in total, we have a setup where we have three tablets. And it is possible that these three tablets might be served, but the leader for these, the T-server leader for these three tablets may be on different nodes. It could be on the same node, but it could be on different nodes as well. So in the streaming phase, when the Yugabyte connector, what the Yugabyte connector does is it contacts each of the relevant tablets. So it knows that it's got to do the streaming for the orders and order lines tables. It figures out which are the tablets to reach out to, and it reaches out to those respective nodes and asks for the changes. Now, on the wall, the write-ahead log, the transaction log, which I think I should mention here that in Yugabyte, we have a wall per tablet. And that's what you see in this picture, these rectangles out here. This is your wall. This is the wall for tablet 1 of order lines. This is the wall for tablet 2, and this is the wall. So each tablet has its own wall. And the streaming phase is essentially going to rely on the wall to figure out what the changes are. So that's the way the changes get identified. And then when the connector contacts the tablets and asks them to give their next set of changes, each of them sends back these changes. What the connector does next is it sort of does a merge sort. Basically, it groups this transaction. All the yellows, by the way, the yellow corresponds to the second order transaction. So it groups these transactions, it collects the pieces of the transactions from each of the tablets, puts it together in the right order, so thereby getting the right order within the transaction, the intra-transaction ordering, and writes it to the Kafka topic in that order. And this is what we saw. This is a snapshot of the control center UI. So this reads bottom to top. So the sequence in Kafka, the offsets are in descending order, top to bottom. So you got to read this bottom to top. And you can see that the orders record went in first, and then you had the order lines. In addition, what the connector does is it writes out boundary markers, so the begin and end, to identify that, okay, all of these happened together in a single transaction.
Yeah, in many ways, Anand, that slide that you had before, if you could just, it kind of captures the challenge of building transactional CDC when your source database is a distributed database, where the transaction log is not a single linear log, but distributed across many nodes. So yeah, this brings a lot of clarity to that. So thank you.
Now, when we move to the inter-transaction ordering phase, so you okay, maybe I think let's go back to the demo. So what we'll do now is we'll actually put in two transactions. So far, we have seen only one transaction being streamed out. Now, let's suppose there were two transactions happening sort of like concurrently. I'll try my best to do it. I mean, I can't really do it concurrently, but I'll sort of give it a shot. Let's say, okay, you have order 4. Okay, wait. Order 4. And I have this here. Yeah, and this is order 5. and I'll commit order 5 here before I meant to run it at the same time, but it's okay. And then I commit order 4, of course. So you've got your 2 extra orders, 5 and 4 here. That's fine. That's all. And you also would have got the corresponding line items. So essentially, okay, anyway, we'll come back to the slide. I think there's more value here. So what I meant to convey is when you have concurrent transactions, or obviously there are going to be concurrent transactions going on. Now the records from the transactions might be interleaved in the wall, as like you can see here. So by the way, all the green records across the 3 tablets belong to the same transaction. All the blue belongs to the same and different transactions. So the green records belong to your transaction order 4 and your blue records belong to transaction order 5. And so your picture inside the wall is like this. And let's suppose that transaction 5 commits before transaction 4, which is what I did, which is what I did while entering those orders. So what happens at this stage? Once again, streaming phase, the source connector, it's going to go back to all the tablets that are all the relevant tablets and ask, okay, what do you have? What's your next set of changes? Now, what each tablet does is it sends back the changes in transaction commit order. Now, the fact that transaction 5 committed before transaction 4 obviously is tablet independent. So each tablet will send back its blue, which is your transaction 5, or all its blue changes before its green changes. So this is sort of the way each tablet has a role to play. That's what I'm trying to say here. In the consistent streaming phase, they will send back changes in transaction commit order. Now, what the connector will do is it collects these changes similar to what it was doing before. It will collect all the blues together. It's like pretty much like a merge sort. It collects all the blue transactions together and sorts them, which we already saw a little earlier, to get the order within the transaction. And then it will write out the blue changes to the Kafka topic, and it will do the same thing for the green changes. So essentially, the ordering is the main approach that is used during consistent streaming to enable consistent loading of the target. And how is that going to happen? Of course, that's because if your sync connector can take advantage of the transaction boundary marker information on Kafka and use a single transaction to write all changes belonging to a transaction. So, okay, so you have changes within 2 boundary markers. These represent changes coming from a single source transaction. And with this information, your sync connector can transactionally apply this change to the target system, thereby moving the target system one consistent state at a time. And that, in essence, is the idea, the broad idea, the 2 phases: consistent snapshot, the establishment of a consistent point, and using that as the initial point for the target system. So basically, you get to that initial consistent state at the end of your snapshot phase, and then you maintain consistency by replicating source transactions in order. And in order to do that, the connector plays a role by gathering all the changes from the transaction. The tablets themselves change the send changes in transaction commit order. The connector collects the changes belonging to the same transaction from all the tablets, puts it together in the right order, intra-transaction order, and then writes it to the Kafka topic. And this is why there was a need for a single Kafka topic, because all the work that the connector is doing, essentially this ordering work that it does, this inter and intra-transaction ordering work that it does, if you want the sync connector to be able to leverage that, then they have to go to a single topic. You have to go to a single topic because that's, in fact, a single partition of a single topic, because that's where the ordering is preserved. And then the sync connector can just look at the boundary markers and do whatever, and then just do the needful, just transactionally do the apply. So in a sense, this is the these are the fundamental ideas behind how transactional CDC achieves data consistency. Well,
Anand, two questions.
so let's
One,
look at, yeah.
Anand, first question is, were the topics, this is coming from the audience, were the topics manually created or automatically by the Debezium connector?
They automatically get created.
Okay. And the second question is, suppose I didn't care about the relative order of transaction 1 versus transaction 2, but I cared about all the components of the transaction, right? And the atomicity of a transaction. Is it possible to like maybe just do topics partition by transaction ID or something as a way to like avoid a single partition or a single topic hotspot?
For scaling it, right?
Yes.
Yes, if you don't care about inter-transaction order, you just want the boundary. Yes, yes, that is possible, and I'll get to that in the configuration section. There is a
Got
custom
it.
flag.
Thank you.
Yeah. So coming to the API and the configuration, so to create a stream, we use the YugabyteDB tool, and like I mentioned a little while back during the demo, we use the API that is used as a create change data stream API, and the last argument is the one related to the snapshot option. So I've seen that. We'll just proceed to the more interesting aspect of the configuration. So this is what was happening in this in the script that I used to deploy the connector. So the connectors get deployed. Essentially, it's essentially a REST call, but the interesting part are the connector configuration parameters. So the first thing we'll look at is the configuration for the connector that was used for moving the snapshot data. Now, the snapshot data can be moved in parallel. And we had 3 tablets. And if we want full parallelism, then you can use this tasks.max property to sort of reflect your degree of parallelism that you desire. You have 3 topics. We went for full parallelism and we picked 3. It doesn't have to be 3. It can be a little lower than that, depending on the resources that you want to allocate. But essentially, you have a way to control this. And the other point I want to mention about moving snapshot data is that it is resumable. So in case the connector goes down and it restarts, then you will continue moving the transaction data from where you left off. So it happens in parallel and it is resumable. So and the snapshot mode is to be mentioned as initial only in the snapshot connector. The streaming connector, you mentioned the snapshot mode as never. And here are the two properties which are important for consistent streaming. One is the transaction ordering, and this is the setting this to true is what makes your connector actually do that ordering work. It do that inter and intra ordering work. And setting provide transaction metadata to true is what tells the connector to publish the boundary markers.
Got it. Yeah.
For consistent streaming, like I mentioned a little while back, it is important to have one topic if you desire that inter and intra order. That's basically the consistent streaming. And so what happens is you have to set tasks.max as 1. And you use this reroute transform to move all the, to ensure that everything goes to this topic. In this particular example, the name of the topic was DB server 1 all events. So all the changes were going into this topic with this name, DB server 1 all events. And coming back now to the question that you asked, Kannan. So there's a lot of flexibility in the connector. So even though your stream is created at the database level, the connector allows you to specify the subset of tables in the database for which you are deploying this particular instance of the connector. So if you want consistent streaming for only these 2 tables, you can just specify this. And if you don't care so much for strict ordering in other tables where the consistency requirements are weaker, it's fine that you don't have as strict a consistency requirement. Then you can deploy another connector and specify the rest of the tables over there. So you have flexibility in the manner of deploying connectors. So you can get at the same time some consistent streaming going on and the others being done without the requirement of that level of strictness for consistency. So that helps to scale your solution depending on. So you balance it out where there is a real hard strict consistency requirement, you go with consistent streaming, and where there is not, you can use a more scalable approach. And that's pretty much what I had in terms of release information. Consistent streaming has been there for a while. It's been there from the 2.18 release onwards, and it's an early access. Consistent snapshot is just coming out shortly. I think it's 2.22, and it will be a preview feature.
All right, thank you.
In terms of the future directions, we have plans to be PG compatible. We have plans to be compatible, PG compatible with logical replication. In some ways, our semantics in terms of getting the consistent snapshot when you create the stream, or in consistent streaming when you do this inter and intra transaction ordered, you order the changes in that. Those are all already in sort of sync with the semantics that PG logical replication offers. But we will go for the SQL API, for example, for the entire CRUD. For instance, instead of create stream, it will be create replication slot, exactly the way it happens in PG. And even in consumption, we will follow the protocols that are part of logical replication, like the streaming replication protocol, the logical streaming replication protocol. So that's about it. So that's all I had.
No, fantastic. Yeah, thanks for really giving a tour of both the little bit under the hood and the value above the hood of what this feature delivers. Very well explained. Thank you to everyone that joined us. And have a great rest of the week. We'll see you on another episode of YFTT next Friday. And Anand, over to you also for any closing comments.
Yeah, thank you. Thank you to everyone for joining us in this session. Yeah, there's some references, some links here to the documentation. You can see where you can get more details about things that we spoke about today. And as always, if there are any questions, feel free to post on the Slack channel. Thanks once again. Thank you very much.
All right. Thanks, everyone. Signing off. Bye.